moment, proceeding for a while and then stopping, has to be somehow an approximation to a multi-charge situation, and can't really tell us much about the core construction of this interaction, electromagnetic interaction. In the same spirit, let me see if I can get that, one of the motivation for the whole thing is to come up with a story that enables us to integrate electromagnetism with all the other theories of physics.
Can you magnify?
Sorry, what can I do?
Magnify.
37.8%, perhaps increase the percentage to,
Oh, here.
yeah. Try 75.
Oops.
Perhaps a bit less.
That's nice.
You think that's nice? You can centralise it.
How's that? Is that okay?
That's better. Yeah.
Try 75 and then
It's 60.
we don't have a 60.
Well, you can
You can write there. No, you can write. They are not.
50 was okay.
No, take 60. Take 60, type 60.
Oh, type 60 in there. Okay. Yeah, I'm just trying to give you some motivation for why we worry about this sort of thing in quantum optics. The electromagnetism is not well combined with the other theories of physics. In fact, electromagnetism is not even completely formulated all by itself. That is to say, Maxwell's theory, which is of course the mother of all field theories, does not lead to coupled equations of motion for simple point charges. Probably the simplest, most elementary electromagnetic interaction would be between 2 point charges. If one attacks this problem with Maxwell's theory, what you would say is that one charge is a current, solve for the fields at the position of the other particle, apply Lorenz's force law there to get the interaction, and then do the next step, namely consider that particle a source, calculate the fields at the position of the first charge, and so on, and then go back and forth until you get an approximation that is acceptable for whatever task you have. An ideal solution, a complete ideal solution, according to the mathematicians, would be instead some formulation that leads to coupled equations of motion, and that then have all the nice properties of coupled partial differential equations, or whatever they turn out to be, and you can then apply the machinery of abstract mathematics to determine whether or not a solution exists for this coupled system, and so on. That we don't have yet, really. An interesting point not to forget. If one writes down for this very simple problem, all the Maxwell equations, all the appropriate Maxwell equations, and the appropriate Lorentz force law, he sees that he has the wrong number of variables for the number of equations. So if you eliminate the superfluous variables, so to match things up, the variables you end up eliminating are the field variables. That tells me that the field variables are not ontological items. They're simply aids for calculation or aids for doing the problem, but they're not fundamental. They're concoctions that we have to help us explain what the fundamental interaction.
Use the thing on the right, the scroll thing.
Yeah, but I have it fixed up so that it should.
I think once you change the setting, that screws it up.
Yeah.
So that's what we found in the past. You have to use the.
Oh, I have to use this.
Yeah.
You think that's?
No, it's with the other people found the same. Once you set it to a certain size and you change it, it doesn't seem to work.
No, doesn't. There's no line. Okay. Okay. Well, this is okay too. No, it isn't. That's the first one.
You need to scroll down on that.
Well, now maybe it does work. No, it doesn't work.
Just have to do it by now.
click on the screen, no, not,
Well, I should, when I hit the X, it should
click
bring
on
up
the text.
Huh?
Click on the text and then press page
I
down.
mean here,
No, not this. On the text,
on the text.
yes. And then page down, page down.
Page down.
Oh.
Now,
You just have to do what you can.
why don't I kill it and start over?
Yeah, go back.
You set it to one thing setting, it won't work for another one.
What do I do? Control, okay, there we go.
Other speakers have found the same.
Still doesn't work. What if I start this way? We're back to at least working.
Yeah.
Okay, how about, can I, no, I can't, this doesn't go up. That goes up a little bit, but then it's out of it.
Just have to wait.
Okay, we'll have to live with this. It doesn't matter anyway, I'm not gonna show a lot of stuff. It's just for the sake of having something to distract your eyes
Change the setting.
and remind me what I want to say. We've already talked about that to the extent. So now, anyway, the current dogma, of course, in electromagnetism is that we have maybe waves. But I think there's no waves. Waves are collective motion of something. So you have to have a thing, a something, to wave, and that's usually labeled an ether. And then by making models of the ether, you actually jump on the first car of a train called infinite regress. Because as soon as you want to do an ether, then you've got to explain what's the ether made out of, and so on and so forth. So that's not really progress, although it may be useful for massaging the thoughts and the symbols so as to come up with better equations or different equations for a particular thing. So I'm not arguing the utility, I'm really arguing here that by not paying attention to exactly what these words mean and what they should convey, we are misled in terms of the fundamentals of the theory. And that may be for particular problems, especially when the primary question has to do with the fundamentals of the theory, it may be poison. Therefore, I'm playing this game of being very rigorous about exactly what we're talking about. Photons, too, useful concept for quantum electrodynamics or whatever. But once again, the photons, the words don't really make sense. A photon has no location. People say, what is it? Well, maybe it's a mode of it's an energy level of the mode. Then they put the mode in a box and let the box do something, go to infinity or go to zero or something. But the boxes are all artificial, so the meaning of what that means, the meaning, actual lexicographical meaning, is really concocted. We're using a lot of words that don't really add up. And so I think that tells me that probably the electromagnetic interaction is not, that this is not giving us any guidance into the fundamental aspects of electromagnetic interaction. Let me go on now. If I can make this go on. Beam splitters. Okay. With a beam splitter, of course, this is nothing new for anybody, but of course you have a source and outputs. In fact, we don't know what happens between the input currents and the output currents. That's what we're talking about when we talk about photons or waves or whatever, is what happens between these currents. In fact, everything we know about electrodynamics comes from analyzing these currents, and then we imagine what transpired between the currents to explain why the currents do what they do. In textbooks, then, we have such a story for the two outputs of a beam splitter. You say you see a blip in one channel and you don't see anything in the other channel, or you see it in vice versa and so on, and these are nicely separated, and it's claimed that shows that photons cannot be divided. So what I would like to talk about today is a proposal that seems to me to be reasonable to test this idea and see whether or not this shibboleth that's been repeated forever actually makes some sense. And of course, if you look at this a while, what you discover is that a real laboratory data looks more like this, although that's not exactly faithful to the way it looks. But the point is that in any case, you don't see what I call the textbook output. What we know about the whole story is that each pulse, each incoming pulse is, say, so long, it hits the beam splitter, and then we have pulses that are, again, have a certain length, and that at some point, not here, this is the input, at some point in the output, during that pulse, a photoelectron will be brought up from the valence band into the conduction band. And then that photoelectron will be amplified, triggered, and counted. But it occurs at some random point in there, according to the usual theory. Now the fact is, though, that these two pulse lengths with the, say, the instant of seeing the photon, is such that the photons never overlap, even if the situation that's being considered is such that you would expect that they would overlap, and they never overlap because there's a statistical effect in the detection of a photon. So the photons are always, no matter what the story is, at different places in the pulse length. Now, this is the point I just made, namely that the pulses are always in a different place. So you can't argue that failure to see exact coincidences is evidence that photons haven't been split. Because even if they are split, you wouldn't expect to see perfect coincidences. A coincidence, therefore, in these types of experiments is always defined in terms of a window. And they say we have a coincidence if both hits appear within the window. And so what I propose here is studying the dependence on the window length. Those two situations we can consider. If the pulses in fact are split, then there will be some correlation between these two evident in there, because the pulse is split, so this would be half of the input pulse, and that would be the other half of the input pulse, and the two things that will correlate exactly are the unknown pulse head. These 2 points. However, that is not observable. The only thing that is observable is the point at which the photon is generated. Nevertheless, each photon has been, or each photoelectron has been elevated at some point within that pulse length for which the pulse had an identical head, if it's split. If it's not split, then, if it is split, then of course the probability has to be written in the form of an independent probability times a conditional probability. But if there is no correlation, if photons are not split, then any coincidence that happens within a given window definition has to be an so-called accidental. It has to be the result of independent photons, independent photoelectrons, or photoelectrons generated by independent pulses sent into the splitter. It's just an accidental. In that case, the probability of a coincidence is simply the product of the two probabilities, two absolute probabilities. So the challenge now would be to work this out. Now what I did, you see, this is a statement, again, how you would calculate the probability of a coincidence for two independent. There's a little, this is a little mathematical program that does some of these integrations and so on and so forth, and you can see what you get. And here's a mathematical program that does the integration when for a different, the previous one actually was for a, maybe it doesn't, yeah, okay, all the better. If one calculates the probabilities, then the straight line is the dependence of a the coincidence on window width. As you reduce the window width, it just goes down linearly. And that's because you're just opening the window and closing the window, and if something happens to be there, fine. If it's not there, basta. And on the other hand, if you have correlated hits, then you have to multiply the probabilities of the distribution of these points in the pulse length. And of course, there are different possibilities for different theories on what's going on. This is supposed to be an ordinarily exponential decay integrated once, so as the time goes through the pulse length, the probability that the pulse occurs at this point will be equal to that, and so on and so forth. It might be a Rayleigh distribution, meaning x e to the minus x, or t, say, e to the minus x. If you integrate that, you'll find something like this. So if you have these kind of probabilities, then the probability of a coincidence will be the product of this in each channel. And that's what this curve is. And this curve, by virtue of being concave from the top, means that if you divide one by the other, you get this divergence. And that's important for some other experiments. But the main point in my presentation is that if we generate long strings of data from a beam splitter, and then compare these statistics for two series of time events. One created when you know you have no coordination, because you take one stream of data and maybe compare it with itself and an offset. Then you know that all the pulses have to have been generated by independent, all of the photoelectron arrival times have to have been generated by independent photon arrivals. So that would be an uncorrelated. That would give you one standard to compare with. And then you could compare the output of two channels and see whether or not it exhibits that concave structure. If it does, then you've got a way of saying that photons indeed are split. Now, I don't know what's going to happen if this is carried out. I rather hope it shows that photons are split. But since I haven't done the experiment and know of no one that has done exactly this experiment, I don't have the answer to that. But I'm trying to elicit an interest in it. And if you have any interest, please jump in. I have very little more to say except to ruminate a little bit on the position of this study in a larger program that I'm trying to carry out, namely to study the statistics of the photodetections used in testing Bell's theorem in so-called EPR experiments. According to that, let's see if I can bring that back up. Yeah. According to this sort of analysis, as you reduce the window width, which they do in the experiments, with the intention of purifying the data set, they believe what they're doing, and the motivation for compressing the window width is to purify the data set by eliminating accidentals. They believe that by reducing the window width, they are increasing the likelihood that they have true coincidences, which seems very reasonable. However, if this math is correct, or if these combinations of ideas is valid, then what they're actually doing is exactly the opposite. They're eliminating any true coincidences in favor of accidentals. In which case, the set that they have is not the set that fit the hypotheses of a Bell theorem, but the set that does not fit the hypotheses of a Bell theorem. And that's very interesting because elsewhere, in analysis of Bell's arguments for deriving his inequalities, it turns out that what he was actually doing when he thought he was encoding locality according to the fundamental principles of probability theory and the definition of what they do, he actually inadvertently encoded statistical independence. But he's testing Bell's theorem with things that are deliberately statistically dependent, where there is correlation. But if this story is true, then the reason he thinks he's seeing a good signal, or the reason the experimenters think they're seeing a good signal, is because actually the experiment is selecting just the wrong set, which happens to give the expected answer. Yeah. So that's the sort of the context in which this whole thing is about. Now, I haven't really been able to, one other little interesting thing is, on this whole story, is we all know about Mauss's law, right? The intensity of a beam is equal to, of a polarized beam going through a polarizer, is equal to the cosine squared of, say, the difference between the angle of polarization of the signal with the axis of a polarizing filter, squared, cosine squared. There's another formula that comes up in quantum mechanics that has the same form. It's alpha minus theta, but in this case, instead of one angle pertaining to a signal, both of these angles pertain to the settings of the polarizer, irrespective of the signal, of the two signals. They're talking about the correlation of the signals going right and going left. You have a source that produces these correlated signals, measure the polarization on both sides, and then compare for coincidences. Then according to Bell, those coincidences should fit into his discriminator equations one way or another, and show that you have to have some kind of non-local interaction to satisfy everything. Now, the fact that these two look alike, however, does not mean that this formula, namely the one pertaining to the correlation, is Mauss's law. It's actually not Mauss's law, but it has the same form. But it's sort of Mauss's expression of the correlation. But to go from here to there is a bit of a problem. And the question is, how does that happen? If you look at how that happens when you do the quantum calculation, you find that there's an integration in there, an average. And so the issue becomes how to effect this average when doing simulations of a Bell test. And that's the context in which this whole program that I'm trying to describe here arose. So I'll be happy to take questions, brickbats, whatever. Please.
I'm trying to say this in a way that I hope you won't misinterpret.
Okay? You won't be the first person to throw brickbats. That's what you're
Have you been made aware of, for example, Feynman's lectures on physics?
Sorry?
Feynman's lectures on physics, which were published in 1965. Feynman's lectures on
Physics, yeah, but he has many. You're talking about the textbooks?
I'm talking about the three red.
Yeah, right, yes, I have copies.
Maybe it would help you to get over what I fear may be some basic misunderstandings. He has a very beautiful description of why you don't need to worry about any of this stuff. And you will even find, I believe, back reference to experiments that were done in the 1920s, which, when they were first explained to me, were completely revelatory, or whatever the word is, by a very eminent professor in, of all places, Oxford, when he said he did the double-slit interference experiment using a conventional light source and a single slit, in which he turned down the intensity such that he was absolutely sure
So he had one at a time.
that he had only one photon at a time, and then sailed his yacht around the United Kingdom, leaving the experiment running. And when he came back, we saw an interference pattern exactly. Now, why do you have any problems with any of this?
I don't.
Because you're demonstrating to me that it worries you that photons should or should not split.
Yes.
Yet, I would not have been able to show you a Higgs to gamma-gamma decay if photons split. So I just don't understand it.
Well,
Because your coincidence windows are exactly what makes a trigger that tells you about Monta interacting. So you're rattling my timbers, perhaps I'm wrong. You're rattling my timbers terribly.
well, I appreciate that.
And I appreciate the fact you are, but not to the extent that you're undermining.
I'm only passively aware of all the machinery that goes on at a deeper level. I have come from the fundamental level this far in electrodynamics,
Yes.
and I claim that at this level there's a problem. In order to go on, this is not quantum, nothing here is quantum. And I
It's
argue.
quantum. Photons are quantum.
Why do you're arguing the photons are, because they're digitized, right?
No. Well, all right, if I may just ask one very direct question.
Please.
Specifically to what you said. There is a photomultiplier, okay? And you talked about light coming in and liberating one photoelectron,
Right.
which generates through a cascade
Right.
amplified current.
Exactly.
Right. Now, do you dispute the fact that it requires one photon to liberate one photoelectron?
What I notice is that electrons are digitized, and that
What do you mean digitized?
they come one by one, they're countable. There's no half electron.
True.
There's no quarter electron.
Just as there isn't photons.
We don't know that. All we know is, that was the point with the story I made, pointing out that all we're doing is putting currents in, taking currents out.
No.
We're not looking at photons. You never see a photon, you only see a photocurrent.
I have seen photons individually.
How?
Oh,
With a photocurrent, with a photodetector,
I
right?
have taken a phototube
Right.
in which I have plotted the dependence, the way the photoelectric effect goes, as a function also correlating that with a single pulse on a scope in time with that which generated the photon. They happen to be gamma rays, actually. So what I'm just disputing is that you're not barking up the wrong tree. I'm sure you're addressing an issue that should be addressed somehow, but you're barking up the wrong tree from the wrong perspective, from where I come from and where 99.9% of professional physicists come from.
Okay, let me back up a little bit and throw another argument, counter-argument back at you. We're going to talk about photons now, we're going to talk about electromagnetism, okay?
Yes.
Electromagnetism, when you describe quantum mechanically an electromagnetic signal, you have actually three variables, a K vector, and then you have two orthogonal polarization vectors, right?
In an object that responds to electromagnetic fields.
If you write down expressions for the wave function for an electromagnetic signal of some kind, you call it a pulse, you call it a photon, you can use any word you want.
No, I'm specifically saying to you that it is a mathematical expression for an electric field and a magnetic field, and that you're going to produce a signal from the response of the detector, which will move electrons around, generate currents, and generate voltage. Right?
Right,
That's
now
what
let
you're-
me make my argument and then we'll go on. Okay. If you write down the expression for a electromagnetic signal, the wave function, electromagnetic signal, you have two aspects. One is the orthogonal in the plane perpendicular to the K vector, and the K vector. Now, in the K vector direction, there are two variables that are quantized, namely the spin variables, phase and amplitude. They're quantized. What's happening there is quantum mechanics, right, left, and middle. These two vectors, the two polarization vectors, call them vertical and horizontal, first of all, are not Hamiltonian conjugate variables, and they do not suffer Heisenberg uncertainty. The phase and amplitude are Hamiltonian conjugate variables, and they do suffer Heisenberg uncertainty. What that means is that all the phenomena connected with the two variables that are quantized need to be analyzed in terms of quantum mechanics, but the two variables of vertical and horizontal are not quantum entities. Everything that happens in that phase, in that plane of polarization, is described or encoded in SU2 structure. SU2 was worked out in the first instance by Stokes 50 years before Heisenberg's father had a glint in his eye. So there's absolutely nothing about quantum mechanics in that plane. And all of the experiments done with maybe 2 exceptions, all the experiments done in quantum optics to test Bellston are in that plane. They're trying to fathom the fundamental properties of quantum mechanics in a plane in which there is no quantum mechanics. So this is heterodoxy, of course, and you would find lots of support on the editorial staff, the physical reviewer, all that, but they don't. None of them have prepared to put an argument on paper that shows that that's wrong.
Okay, we'll just leave that argument for the moment. Did you have a different point to make?
Well,
John?
I don't agree that there are no waves, but if there are waves, when you're talking about slits and photons,
Yeah. Okay.
can I just say, where is the photon?
Yeah, when we have Gauss's laws there forever, there's an interaction, there's patterns there. So we can write
He hasn't put his question yet.
I heard his question. I know what it is. I anticipated. Let me answer this, and then you can go on. Okay, if I haven't answered your question, you write that down. So then you have a mathematical expression which encodes the patterns of all of this. Now we know from Fourier analysis you can always break down any function in terms of Fourier components, right? The solution space of every Sturm-Liouville equation is Hilbert space, and therefore it has eigenvectors in the whole story. And the equations of electrodynamics and the Schrödinger equation all Sturm-Liouville equations. So their solution spaces have, but none of those eigensolutions are actually ontologically physical, no matter how useful they are, no matter how useful, because they don't individually satisfy the boundary conditions. If you want to find solutions to the wave equation, quantized or not, that satisfy the boundary conditions, you then wind up talking about coherent states. And all the others don't. For example, the Hermite polynomials for a harmonic oscillator don't oscillate. But the coherent functions built from them do. Did I answer your question?
No, I didn't think I understand your explanation.
Can we try a question from John?
Not for this, I think you are missing a major point. Always diffract. You cannot give me a wave that doesn't diffract. And as soon as you have diffraction in Maxwell's equation, you have to compose the plane wave out of TE and TM waves. You have 2 lots. So you don't have just your orthogonal things in your plane. You have TE with its 2 orthogonal possibilities. You have TM with its 2 possibilities.
I understand all that. Know all of that stuff. Used to work at NASA, worried about all that, going to Mars and all that stuff. I'm very familiar with all that. My argument is the same that I just gave here. You can analyze these signals in those terms, but they are not ontologically necessarily the things that really is happening. And you have to, in each case, you have to satisfy the boundary condition. Now, the engineers have worked this out. They pick on modes that generally do satisfy some standard boundary condition, either a waveguide or
But
something
they're
like
perfectly
that.
entitled to do so.
What?
They're perfectly entitled to do so.
They're not only entitled, they're required. A solution to a differential equation isn't a solution to a physical problem unless it satisfies the equation and the boundary conditions.
I suspect this is an argument of cross purposes in some way. Do you have another question?
I have a completely different question. I comment to the Ballard's law. And I think this Ballard's law is something which is important because in respect to the EPR experiment. And I think it is in some way uncertain that this is true because it is what we do to check it. We have a polarizer and an analyzer. And what we do, we enter unpolarized.
That's the detector.
Yeah, and then we turn it and we measure the intensity. We do not measure polarity. So and we get then this cosine square law. But what is between both, cannot be measured. We assume that the polarizer makes a 100% polarization, and then the analyzer follows this law. It can be completely different. It can be a cosine law and another, a sinus law and another sinus law.
I agree.
And
That's
then
this.
you have completely different results regarding the EPR experiment. So this is very important. this is a summarized result, but not in the detail for polarizer and analyzer as you need it.
It's all there. I didn't want to go through it. That's all. The issue is not that. The issue is when you have the two angles down here are both polarizer filter angles. Polarizer filter program, you're talking about two signals and you're doing a correlation. Not when you're making a measurement after a single polarizer, sending a signal in through a polarizer and then measuring its intensity afterwards. That's the first formula. This is the correlation formula. In this case, you have one angle pertains to the wave, one angle pertains to the polarizing filter. That's Morris's law, and that no quarrel with any of that. This law also works.
Yeah.
But the question is, how do you relate the two? They look like they're identical, but they're not identical.
But the lower one, the second one, has different logical consequences if you
Exactly.
make different assumptions about why Morris law works and it works.
Right.
And that is always forgotten. That's what I'm
It's different. Right.
See what?
I have a very simple question. Do you think Maxwell theory have a radiation reaction force?
On the source particle,
No, the whole theory have included radiation.
I have a very simple little answer to that is that if you place two charges, say, or you place a charge in a plasma, it will induce a plasma sheath around itself. And so if you accelerate the source charge, then there will be a backtalk from the plasma sheath eventually. And you can actually, very simply, show that the argument that Dirac used to derive the reaction force makes better sense if you think of it as the reflection from the Debye sheath, they call it.
I'm not asking Dirac, I said Maxwell theory.
This is Maxwell theory applied to a plasma.
Okay, hold up there, Brennan. This small won't come again. John Dayton, after hearing this argument, do you think that his polarization vector design form has, like you tried to make it?
I can't discuss this because I don't know what variables you're working with.
Okay.
I don't understand.
This might be better written because it's obviously a deep discussion.
It's not a deep discussion, there's some basic facts that are
Well, basically, very deep.
Vertical and horizontal are not, it's basically true that vertical and horizontal are not Hamilton variables.
We have to stop here to keep
Yes. Can I point out one thing?
Discussing the basic discussion.
The experiment John was talking about earlier with the going on the yacht and everything, was done by G.I. Taylor in 1909. 1909. Okay. Well, that's stimulated a lot of discussion anyway. Thank you very much for that.